Google's new AI can see the world in 4 dimensions. This is a new model by DeepMind called 4D-RT that can take your videos, convert them to 3D output and put them in 4th dimension, which is time. In this video, I'm going to show you how this is going to really change our observation of AI in field of robotics, AR and world models, and what's your take on this significant breakthrough. Let's check it out. Initially, we wanted to let AI models see the world, so image was a good way to represent what's going on in our environment. But there was an issue with image. It doesn't have the definition of motion, the flow of how our environments move. So we had ended up having cameras as a new video feed for new set of information that goes to the AI models that can understand the dynamics of what's going on in our environment. But still there's an issue with 2D videos. Well, they do not represent the 3D construction of the object, it's just a 2D demonstration. We do have AI models that can now reconstruct the 2D objects to 3D, but still we're missing another dimension, time. The 3D objects move through time. This is how our human brain observes our environment. We see a specific object in our environment, we connect the dots between past, present, and future, so we have a holistic end-to-end understanding of our 3D environment through time. That's how we maintain a persistent understanding of our environment. Now, how we can do this, or better say the same thing, for AI models up to even 300 times more efficient than previous solutions. And this is the new AI model that DeepMind just released that is coming with really significant breakthroughs and interesting capabilities. So before I get into the secret sauce and how they do it, I just want to quickly touch on some of the main capabilities of the model, and then we will dig into the further details and see some examples. The first thing they announced is that it can do point tracking. So point tracking means I can see a specific pixel's location across different time steps, so I can predict the 3D trajectory of the pixels even if they are not visible in all frames of the video. Check this out. This is my 2D video input, and you can see obviously they're moving around. There are 2 humans in place. Sometimes the white one versus blue one, they are masking each other, so the objects are not 100% visible in all the frames. But as you can see on the right side, it is truly creating the prediction of 3D trajectory of the movements within this camera angle that it is showing, which is amazing. So imagine that even if your 2D demonstration of your objects in the video are not 100% visible all the time, don't worry, you have the 3D representation of that within this prediction of trajectories. The second thing is point cloud reconstruction. That means when the camera is moving in 2D video, not only I can reconstruct that in 3D, but also as soon as I freeze the time, let's say I'm gonna pause here, I can rotate and reconstruct that 3D in any angle that I want. That means I do have 3D reconstruction beyond just what camera could observe here. And you can see that it's perfectly going through the view of the camera as it was initially located in a 2D video. Not only that, camera pose estimation. It can also change the view of the camera, not necessarily where the camera was at the initial 2D video, which is absolutely amazing. And think about how it will influence fields like robotics, AR, and self-driving cars, and even world models, which are the necessary steps to get into the AGI. Here are some cool examples of that 3D tracking of the points or trajectory of a prediction of trajectories. You can see that again, if objects are blurred, hidden at specific frames, still you can rotate and see the prediction of trajectories, and it has the understanding of depths that colors are showing us into the perspective of the location of the camera. And also point cloud reconstruction, as I just mentioned, you can freeze the time and rotate around the 3D objects. This is another example, the 2D video coming in, and now you see the 3D version has been created and can be rotated. Here's another example. And again, you don't need to necessarily fine tune or provide your training data. The model as is can have that understanding, and just only 2D input would be enough to reconstruct what is demonstrated here as the output. Also, it can provide some long-term prediction, and from long-term I mean the length of the video. You can see that this is great for, let's say, self-driving cameras, that a 2D video has been recorded as we navigate through different streets, and you can see that understanding of the model from the 3D observation of the environment even through this long video process that has been set up in this video demonstration. And from the performance perspective, they're showing that how they significantly got better compared to other state-of-the-art models. And again, they emphasize on the fact that it can be specifically very fast, sometimes up to 300 times more, that can be really used for real-time applications. And there's a secret sauce behind how they suddenly ended up having this significant jump on the performance, which I gotta get into that very shortly. The reason behind that fast performance and also much more accurate is that previous models, let's call it here old ways, or they're not old, but they consider state of the art, but they are prior to this new approach that DeepMind proposed. They were trying to actually reconstruct that 3D objects or put it in order of time with having different components stitched together. For example, they had separate models for just understanding depth. They had separate models for understanding motion or segmentation, and then they do all sort of optimization. So putting all these pieces together not only was causing some issues, let's say here, some ghosting artifacts because objects are flowing around in different dynamics within the time and frame, so you will see some blurriness. And at the same time, it takes some time because you have to run all these components. But DeepMind realized that, wait a second, we might need to maybe totally shift our understanding of how we represent the world and then convert it to 3D or 4D. That's why they announced D4RT. So what they do is that when they take your video, they encode it and they create a representation of all that environment or global scene that is available in the video. So now, if I am here at this stage, this is the representation of my video or my world, my global scene from the input of video, and now it is in the language of the model by itself. So in order to reconstruct that in 4D, what I can do, I can just query this representation, and the query is what will be the location of given pixel, which is a specific object, with a given time in a 3D world. And imagine that simple query will be asked 1,000 times from this global representation. So because you keep asking in parallel all these questions from where that pixel gonna be, where that pixel gonna be, where that pixel gonna be, and then we reconstruct them all together, now we have that 4D representation. And because we do this global scene representation once, we don't need to go through this all encoder again and again for reconstructing everything. That's how it becomes so fast, again up to 300 times more efficient compared to just previous models. And that's how we can have efficiency gained by just having this global representation without stitching different components. So all the 4D representations are coming from one single pane, single model, single approach that gives us depths, 3D trajectories, point tracking, point reconstruction, and everything that we just discussed already. Here's just a better demonstration of what I just talked about already, which is a feed-forward vision transformer that takes your video. It has the self-attention encoder, and this is the global scene representation that I just seen, representation that I just talked about. And then through that cross-entropy decoder, we call it cross because we are keep asking queries coming in as an input, also that global scene coming in as an input. So that cross-attention applied here to get that 3D position from thousands of queries we ask for the given pixel. For the given pixel, we're gonna ask where, when, and from, which is that angle of the camera that we just saw a couple of examples. So this is truly the main skeleton of the secret sauce behind how this model becomes so fast and efficient with just having one component, not a specific different models to be in one place. To summarize what you will take out of this model, it can do point tracking of all the objects or pixels, point cloud that we talked about, the fact that it not only generates a 3D, but it can rotate around the 3D objects within the time that is frozen. Also depth mask, so it can perceive the depth within even the 2D video, and the camera pose that can be changed and reconstructed based on your given input settings. Something to also note that caused the model become so fast is that, first of all these queries that we're asking from that global representation of the scene that we had can be totally independent. So we can decode 1 point or 1 million points without the computational complexity exploding. And secondly, we are decoupling space from time. So the model can predict where point was, is, or will be viewed from any perspective. This is also the secondary reason that why up to 300 times faster that tracking or 3D trajectory generation would achieved by these components. To give you some benchmark ideas of how this model works compared to other ones with similar capabilities, you can see that it is 100 times faster than MegaSam, which is one of the well-known one in the field, 9 times faster than VGGT, and within just 1 frame per second, it can track up to 40,000 tracks. Another issue that you might have seen in other 3D models is that some very tiny details might have been missed because the models pay too much attention to understand the dynamics of the flow of the movement of the object, so it gets blurred or some details are totally missed. So given this example of butterfly, you can see some very tiny sharp components at the edge here. So the model will consider that without sacrificing these details for creating that 4D constructions. So by embedding that 9x9 pixel patch into the query, this D4RT ensures sharp objects boundaries and subpixels precision, capturing the delicate geometry of even something like butterfly wings. So here the details of the objects are not sacrificed because of just creating that reconstruction. So to summarize, one model for everything: depth, tracking, and pose, so no glue code. Second, it's a flexible interface. It decouples space from time so that we'll end up having a much more efficiency and even faster solution because it has parallel efficiency, because you can send multiple queries in parallel for asking that given 3D pixel, given pixel at when and what angle of the camera that we just discussed from that global scene representation. And of course, state-of-the-art accuracy, as we just talked about, some benchmark that is amazing. And here are some more examples of pixel tracking. You can see as I play the video, I can not only rotate this, but I can clearly see the depth understanding plus the tracking of every single pixel from this given 2D video with changing the angle of even the camera. If I click on other ones, you can just go through different examples. I will add a link of all the research blog and the paper to the Discord channel, which is a link of that in the description below. And point cloud, which is again freezing the time and reconstructing the 3D object. We just talked about that already, but again, truly amazing results. And this, as you can guess, significantly improve our AI applications in environments that the model need to observe their surrounding, like again, self-driving cars, AR specifically, and in totally our understanding of world models and how AI can perceive physics or world or the construction of our surroundings that can be a step towards the end, which is AGI. Alright, that was all about D4RT. I hope you truly enjoyed this quick walkthrough and the summary of this finding, and if yes, I would be very thankful if you click on like icon and make sure you share your thoughts in comment section below and subscribe so you won't miss the next video. Thank you so much.